Right, in this short video we're going to look at how we analyse sound with this fella here, which is an oscilloscope. Now an oscilloscope basically is a fancy voltmeter. All it does, it can measure a voltage, but it can display how it changes in voltage varies with time. Okay, so it actually plots a graph, it plots a waveform, which is essentially a graph of voltage on the y-axis against time on the x-axis. So it's a fancy voltmeter. Now connected to that we've got the voltage being produced by a signal generator. So the signal here is an alternating voltage. That's connected straight in here. Now also connected to the signal generator we have a loudspeaker. So this alternating voltage is being used to drive the loudspeaker. So then we have the waveform here is an exact measurement of the sound coming out here. So if I turn it on, first lovely sound, we've got 100 Hertz. So what that means is that is oscillating 100 times every second. Okay, the cone is moving out and back again at 100 times every second. You probably can't see that on the film, but I can definitely feel that through my fingers. Now, the vibrating cone is vibrating the air molecules, they're banging into the ones next to them, they're banging into the ones next to them. So the oscillation passes through the air. Now because the oscillations are in this direction and the sound is travelling in this direction, transverse or longitudinal? Okay, there's a question for you. Right, if I take the frequency right down, we should actually, now that's 10 Hertz, that's the lowest frequency you can go. You should be able to just make out the actual oscillations there. Okay, so the cone is actually moving in and out. Now the lowest frequency audible to the human ear is officially 20 Hertz. Anything below that is called infrasound. Okay, as we can see, the vibrations are getting faster. The frequency is going up, and we can hear the pitch start to rise. Now, one thing I'd like you to also notice is what's happening to the waveform. The waveform gets bunched up, gets more bunched up. Okay? Now that's because, remember, this is a graph of voltage against time. So if the wave's getting more bunched up, it means the time period is getting smaller. The time period for the full oscillations is getting smaller as the frequency goes up. Okay? Now another thing we can change with the sound is the loudness. Now loudness is completely independent of frequency. Okay? Now loudness is all about the size of the voltage, not the frequency of the voltage, but the size of the voltage. Now, hopefully you can see there, if I take it quiet, the oscillations, let's go back down to 10 Hertz. So that's loud, the oscillations have a big amplitude. Okay? If I go quiet, the oscillations have a small amplitude. It's still moving in and out 10 times a second, but it's just doing it a smaller distance. Okay? So 100 Hertz. Let's stick with this. Because finally, I'm going to show you how to analyse the waveform on the screen. Okay? Right, as I said, this is a graph of voltage against time. So if we want the time period, we want the time for one complete cycle. So let's move that over. So we can count the squares now. Right, this is a very important setting here. This is called the time-based setting. This tells you how much time each individual horizontal distance, each individual horizontal square is. Now that says 2.0 milliseconds. So each of these squares horizontally is 2 milliseconds. So how many have we got? We've got 1, 2, 3, 4, 5. One complete cycle is 5 squares. 5 lots of 2 milliseconds is 10 milliseconds. Now 10 milliseconds is 0.01 seconds. Now the frequency, as we know, is the reciprocal of time period, so 1 divided by 0.01 is 100. Okay? Well, I'm going to just do 2 more, and you're going to tell me what the frequency are. I want you to have a little look at this, calculate, but I'm going to cover those up. Okay, right, let's go up to... resolution.